that we started our Laplace transform, and some basic mathematical aspects of the Laplace transform have been discussed. But our objective here is we have to apply the Laplace transform to our electrical engineering systems. And meanwhile, you have some experience in using it in your control engineering. But we will discuss some aspects of Laplace transform uh, in the perspective of using them in electrical systems, particularly electrical circuits and electronic circuits, and even you can use it in electrical machines. In order to do that, we have about two approaches. One, if our input-output relationship is known, then we can apply our Laplace transform there to transform your system into S domain, or your system can itself be transferred into S domain. So this lecture is actually, from this point ahead, we'll discuss how your system can be transferred into Laplace domain by element-wise transformation. Okay, let us, because principally we have our three passive elements in the electrical system. One is resistor, another is inductor, and the third one is capacitor. And we know the voltage current relationship in each of them. If we go to the resistor, then this is how the voltage and current relationship. If we take the Laplace transform in both sides of this equation, this is how the Laplace transform. Okay, only the variable with time is transferred into S domain, but R is not changing with time. So your R will be appearing as a constant there. So the Ohm's law, like something in resistor, is transferred into S domain. This is similar to Ohm's law. R, that means in terms of element, the R in the time domain will remain unchanged in the S domain. Then we have our inductor. We know the current voltage relationship in the inductor. Then if we take the Laplace transform, this is the Laplace transform of Vt. We have a derivative there in this side. So this is how the Laplace transform of this derivative. L is appearing as a multiplier. IL0 minus is the initial current present in your inductor. And if we rewrite the equation in this form, you will see that this will be looking in this form. Now the case is that if we just analyze the thing a bit further, you will see that your V, no matter whether it is in time domain or in S domain, your voltage is volt and your current is ampere. So if this is volt, your left hand side is volt, and then your right hand side is also volt. So the first term of your right hand side is Is multiplied by SL. That means you can consider this quantity SL a single quantity and multiply it with Is, the current. And here in this case, S multiplied by IL, it is also a voltage source. So you can consider that this is also Ohm's law. Here your Ls is analogous to a resistance or impedance or reactance. Your Is is your current, and the second term that originates from the initial current present in your inductor is actually a current source, and it is independent of S. Later we will see how can we draw the electrical circuit using this equation. So an inductor in the S domain is represented by SL, and the initial current in an inductor will be appearing as a constant source in the inductive circuit. And you can rearrange this equation for your current, and you will see that if you solve for current, your current equation will be something like this. That means you will have two current sources there. One is Vs by SL, another is initial current divided by S. Now if we have our capacitor, then we know the relationship between current and voltage in a capacitor. Like your previous case, you take the Laplace transform. Your Laplace transform will take this form. Now this is your current. This is also a current. This is also current. Then this current can be written as Vs divided by Bs divided by 1 divided by Cs. Then this quantity 1 divided by Cs can be thought as a capacitive inductor. So in your time domain, and you can rearrange this equation into the voltage form, and that will be this equation. Okay. So if we want to summarize this table, then in the time domain, we have our R there in the S domain. No change is there. If we have our L, then in S domain, it will be there as SL, but in initial value is also there represented in this way. And if we have our C, then your C in the time domain will be 1 divided by Cs in the S domain. This is very similar to our Fourier transform or your phasor analysis, how we can convert our network into phasor domain or frequency domain. So once your element wise transformation is available with you, then if we have an electrical circuit given, then we can easily replace the element in the time domain to S domain in this way. You can have your parallel architecture as well as your series architecture. Whenever you are using voltage transform, then it will be series architecture, and when we are using current transform, then it will be your parallel architecture. So this is what the architectures. Okay, if we have our time domain representation of an inductor, something like this, an initial current is flowing downward, given by this arrow. Then, according to our earlier slide, you can transfer your network into frequency S domain. Your L will be replaced by SL. Your current will be Is. Your voltage will be Vs. Then a voltage source will be appearing in this polarity as Li0. If your I0 is 0, this voltage source will not exist. So your initial value is translated into the S domain in this form of voltage source. Now, if we use the second version of the equation, solve this equation for current, then we obtain two current values there. One was Vs divided by SL. That current is flowing through the side. And we obtain another current due to initial value. This current is I0S by S. Okay. So in this way, a parallel representation will be there. This current is Vs divided by SL. You know this thing from your very basic electrical circuit analysis. So if we have a capacitor, that capacitor contains an initial voltage in it, V0, then this can be represented by a series architecture of this of this form. Here your Vs would be equal to Is multiplied by 1 by Cs plus V0S. Consider this polarity. If we have this polarity of voltage, and for your series configuration, this would be the polarity of your initial voltage. If we make a mistake here, then your formulation will be wrong. In the same way, if we have a current flowing through this direction, then the voltage present there as a initial voltage will have this direction that you have to be very careful about. And the current direction is this. Now, if we did, that means if we separate the initial current there, then if no, then this inductance L is now carrying no current. It is a current free initial value is already separated there. So whenever we apply a initial condition, then what will happen? This if no current is flowing through this inductor, then what will happen at the time when we change the state, that this inductor will be have like an open circuit. No current is flowing through. Then a current is going there in this other branch. That is actually the initial current of your inductor. This current is going through this branch. So your capacitor by simple transformation of a voltage source into current source will give you this configuration. You know the source transformation technique. Here in this case, your LS is your impedance, or you can consider it as a resistive like something. A voltage source in series with a resistance like something that can be converted into a current source with parallel resistance, something like this. So if we have, this is your capacitor representation in series form, and this is the capacitor representation in parallel form. The polarity and the direction of the current due to initial sources are very, very important. Otherwise, your formulation will be wrong. It is not a very big deal. You need only the knowledge of your electrical circuit of first year to represent the equation in the form of some electrical circuit, either in the parallel form or in the series form. Which form you will use, this is up to you. But you have to choose the form in such a way that your circuit will be, in the transform domain, your circuit will be looking simpler. Consider this technique applied to this problem. I have prepared this lecture from Alexander Sadiku's book, chapter 17 or 18, the Laplace transform application to electrical systems. You can have a look from this book. Now, if we have this thing, actually this is nothing but simple illustrations of application of Laplace transform to electrical circuit analysis. Here in this circuit, no initial values. It has been assumed that the inductor and capacitor has no initial values in them. Then what you can do by using the earlier transformation, your I0 and V0 would be 0. Then you simply replace your L by Ls and C by 1 by Cs. Then you redraw your circuit that and in the S domain. So how to do that? First, you convert your source into S domain. Convert your source into S domain. The unit step has the Laplace transform 1 by S. And your 1 by 3 Farad capacitor would be equal to 1 by Cs. This is what this, C3 divided by S. Your 1 Ls is equal to S, something like this. You have been asked to calculate your V0. What you need to do, you have your two loop there, apply your loop analysis, solve for I2. Once your I2 is available, then your I2S multiplied by S would be equal to V0S. Then you take the Laplace inverse of V0S, that is what your output, V0t. Up to this point, you need your Laplace transform. The later thing is electrical circuit analysis. You can do it by your own, okay? You have to verify this solution. If we solve for our VUS, your VOS will be looking like this. Okay, you write your two loop equations in terms of I1S, solve for I2S. Once your I2S is available, multiply your I2S with S. That is what the impedance of your inductor. That will give you your voltage in S domain. Once your voltage is S domain, then you have this thing with you. What you need to do, you have to take your Laplace inverse. What I have told you in your earlier classes, in taking the Laplace inverse, you will have your equations. Sometimes you partial fraction it, or other cases you can shape the equations in such a way that the Laplace transform of this equation coincides with some of your known Laplace transforms, so that you can make a one-to-one comparison to replace your time domain quantities. This is a quadratic equation. Whenever a Laplace transform is available with quadratic denominator, then you can think that that term can be expressed in the time domain into the form of sine and cosine functions. So by using your elementary algebra, you can easily write your denominator into this form. So once you have a denominator into this form, then this quantity, you know that if we have something with us is equal to omega divided by S plus alpha square plus omega square. What is the Laplace inverse of this term? Hey, are you there?
Yes, sir.
What is the Laplace inverse of this term?
Sir, sine omega.
Only sine omega?
Uh, no, sir. There is a
Why this S plus 1 is there? You know that shifting property of frequency shifting property or a shifting property. So this will be equal to what? A shift is there. It will be equal to minus alpha t into sine square root of 2t, something like this, ut. This is what the Laplace transform inverse of this form. So if you know this thing, then you compare this thing there. You replace your alpha equal to minus 4 and your omega is equal to square root of 2. So this will be the Laplace form of it. What you call Laplace inverse of your voltage VOT. You see that we have a second order system, very interesting problem. You have a second order system and applying what? Applying a DC there, but you are getting an output. That output appears to be a damping sinusoid. If we plot this, how it will look like? If we plot this function, how it will look like? At t equal to 0, its value would be equal to 3 divided by root 2. Then as your value is going down and sine value is 0, so it is 0. So its value is simply decaying in this way, isn't it?
Yes, sir.
Up to this point, your Laplace transform is there. But rest of the things is first year electrical circuit. Be careful about that. So no further discussion will be made on it. You have to get through it. Okay, this is a second order system. For this reason, you see this quadratic factor is appearing at the denominator of your output. But sometimes some other factors can be there. In other cases, if you cannot shape your denominator into the form of your known forms, then you have to apply the general rule of factorizing it. That means this equation can again be rewritten as, this equation can be rewritten as 1 divided by, say, A divided by S plus S1 plus B divided by S plus S2, where S1 and S2 are what? S1 and S2 are the roots of what? S square plus 8S plus 18. So you set your 8S square plus 18 equal to 0, then S1 plus S2 equal to minus 8 plus minus square root of 8 square minus 4 into 18 divided by 2. So this is what your root S1 and S2, and you will see that your roots are getting complex. And because of this complex root, we are getting sinusoid. Okay, so you can go either ways. Either you can apply your sine and cosine form by using comparison that you know, or you can factorize it into your small elementary factors. Then you can easily find that your output will be equal to S A into e to the power minus S1t plus B into e to the power minus S2t. Here your S1 and S2t will be complex, and your and the constant A and B can also be complex. But S1 and S2 will be appearing as complex conjugate. As a result, if we sum these two terms together, it will take the form of this real function. You verify it by your own. Okay, you have the second problem where the initial value is given. And you can see from the network that we have a single energy storage element there, and it is a first order circuit actually. And your capacitor is there, and capacitor has an initial voltage in it equal to 5 volt before application of the sources. Then you have to find the voltage across the capacitor for time t is greater than 0 when your sources are applied. You have your two sources there. One is an exponential source from t equal to 0 to infinity, and another is an impulse. Another is an impulse source with strength equal to 2. If we want to find our, we can easily derive the input-output relationship by in the form of differential equation, but we are not using it. we will be transforming the network into S domain. This is your TD network, time domain network. This is your S domain network, okay, SD type network. How to do that? You convert your source to S domain. You 10 e to the power minus t, it would be equal to 10 divided by S plus 1. This is how you transform of your source. And then you transform of your next source. What is the transformation of unit step function in unit impulse function in S domain? What is the Laplace transform of delta t? ক্লাসটা বন্ধ করে দেই। এই একজন কথা বলো, কত হোয়াট ইজ দ্য ল্যাপ্লাস ট্রান্সফর্ম অফ ডেল্টা টি?
So what?
Then this could be equal to 2a. Now what you need to do, either you can replace your, okay, your resistances will be remaining same, and then you have to convert your capacitor into S domain with including its initial value. Then if we what architecture you can use, you can either use your parallel architecture or your series architecture. It is up to you. But in this circuit, your common sense will tell you that if we apply our parallel architecture, we can use our nodal analysis simply just to find the value of VOT. That in this case, what will happen then? A capacitor will be there. That value will be equal to 1 by CS. You C equal to 0.1. So it is 1 by 10 CS. Then it will, and a current source will be coming in parallel with that capacitor in the S domain. And the value of this current source would be equal to what? C multiplied by V C0. And the direction will be determined by the polarity, because the polarity of capacitor voltage is given in this way. So your current source will be in the upward direction. So this is what from your previous slide, that this is what the current due to the initial value C multiplied by V0. C equal to 0.1 farad and your V0 equal to 0.5. So this current is 0.5 ampere. So you have the thing with you. Now you apply your first year elementary nodal analysis. What will happen? You have a node A, nodes are there in the circuit. জব বন্ধ হয়ে গেল নাকি? একদম পুরা পুরা সাইলেন্ট। How many nodes are there in this circuit?
2 nodes, sir.
Where are these 2 nodes?
Sir, the 2 side of the 10 ohms resistance.
2 sides of this 10 nodes, only these 2 nodes
No, sir.
or these 2 nodes?
Sir, the later one.
Is it not what? Then this node is not needed.
Sir, this is the zero potential node, so
Zero potential node is not considered as a node. If this node is not present, then where your current will go? First year পড়ে এসে এই যদি হয় তোমাদের knowledge, I don't know where you will go. Then you have your node, you identify, you write your nodal equation. Your objective is you have to solve your V0s. Then once your V0 is available, then you take the invert that will give you the voltage in the time domain. Because I will not solve the circuit from this point ahead, because this is your first year task. Eventually you will have your output. That output is equal to this, and we know that your output will contain exponential because your inputs are not persisting for long. For this reason, your output will also be a decaying something, because the impulse response of this specific type of network cannot be everlasting. So for this region, what you can do, you take your thing there, and you see that in this case, this was your factor. You can easily partial fraction it. Then two terms are there. Take the inverse by simple comparison. This is what your output. And your output contains two exponentials. One exponential eigenfactor is very similar to your input, but another is coming due to your system. Your initial values can be given in your network, or your network condition is described in such a way so that you can extract the initial values from your network. I have discussed the thing earlier in time domain several times. So you see that in this circuit, your switch was at position B for a long time. Then at time t equal to 0, switch was transferred to position A. You have to find the voltage across the capacitor for time t is greater than equal to 0. You please solve it by your own. You have to extract the initial values from the earlier state. Then you have to apply the initial value to the later state that begins at t equal to 0 ahead. Then you can easily find what is the voltage across the capacitor by using Laplace transform. It is a simple first order circuit. Okay, you have another circuit there. Here in this case, another I have to consider tell you one thing, that if you have your network transferred into S domain, that may contain dependent sources, independent sources, whatever it may be, whatever you learned in your earlier electrical circuit course can be there. So once it is converted into S domain form, then all the network theory, network principle that you have learned in your first and second year will be 100% applicable there, even network theorems. You can apply your network theorem, Thevenin, Norton. You can apply your superposition theorem there. You can apply your what we call nodal analysis, loop analysis, whatever thing you need, you can apply. So in this problem, your capacitor in the voltage is also there, your inductance currents are also there. Then those things are mentioned in this problem. What you need to do, like your previous problem, first thing is you have to transfer your network into Laplace domain. Once we transfer our things into Laplace domain, then you see that, okay, here in this case, you see your capacitor voltage is there, but your capacitor, what type of equivalent architecture is used in the S domain? A series architecture, isn't it? What happened to it? A series architecture is used in it, and your capacitor voltage is there at time t equal to 0, minus 1 ampere flows through the inductor and plus 5 volt is across the capacitor. That means both you think contains the initial values. Here in this case, this is what the generic transformation. Okay, here your parallel architecture is used for your capacitor inductor, and series architecture is used for capacitor. You can use your parallel architecture in your capacitor, no problem. So if we use your parallel architecture in your capacitor, for your capacitor, what will happen? Then you will have a capacitor there in series, in parallel with a current source, isn't it? Something like this. Which architecture will appears to be simpler? You have your capacitor replaced by this architecture, and your inductor is there. You are replacing the inductor by this architecture. Something like this, and rest of the circuit is there. Okay, you have a voltage source 10 divided by S plus minus, something like this. which configuration is a bit easier to solve? Okay, no idea. Then you try to explore it, that which configuration is easier to solve. Here in this case, this is what the general transformation. The direction of this current is there in accordance with the general transformation. Direction of this voltage is also in accordance with our general transformation. So these voltage source will coincide with the given initial values, but this current source will not coincide. Reason is that your current is -1 ampere. So you can use this configuration with replacement of I0 equal to -1, or you can reverse the direction of your current, put your I0 equal to +1 ampere, both the same. Then whatever analysis you prefer, you apply there, either nodal or loop, whatever ways you can go. You will find this equation there. Then you can solve for your V1, that is what your V1, like your previous problem, then take the inverse. So you see that these solutions are doesn't need any new knowledge. Only the thing is that once you know the transformation of the network to S domain, the rest of the things are with you from your very beginning of this university. So you can proceed with doing the thing. Lots of problems are there in your book. So try to solve them. This is a problem related to Thevenin type equivalent. Okay, if we have a network, that network appears to be a bit complicated. What you can do, you can use your Thevenin equivalent network, what you have done earlier in the case of electrical circuit in your first year. What you need to do, if we want to find the voltage VOT, for example, although many of you has a problem in electrical, even some of you cannot write Ohm's law correctly. So this is what the problem with you, but that cannot be solved at this stage. So what is happening there then? If you want to find the voltage across the 5 ohm resistance, then what you need to do, you can solve the network directly, no problem. But you can use your earlier learned technique to make your solution a bit simpler. How to do that? The generic method is what? You have to disconnect this branch through which you need to find the current, or across which you need to find the voltage. After that disconnection, your network will be looking like this. Then you replace your network looking from terminal A to B by using Thevenin equivalent. Once your Thevenin equivalent is built, okay, then this is what your Thevenin open circuit voltage in terms of S. In the S domain, then you can use it as an independent source is there. Then you have your two techniques to find your RTH. Either you can apply a test source. In that case, this independent source should be deactivated, or you can short circuit terminal A and B, find your short circuit current. Then your RTH would be equal to VTH divided by ISC. So in both ways you can go. So in this here ISC is used, so it is short circuited and solved for this circuit. Then ISC was available, VOC was this. Then what you need to do, you replace your network into a simple Thevenin equivalent that will contain a voltage source equal to the Thevenin voltage, and an impedance in series with that voltage is equal to the Thevenin resistance, that can determine by dividing your Thevenin voltage with short circuit current. So this is what the resulting electrical circuit. Then you apply your simple potential divide rule there to find your VO. Your VO would be equal to 5 multiplied by VTH divided by 5 plus ZTH. Your ZTH is in S domain, your VTH is also in S domain. So eventually you will find your voltage VO in the S domain. This is what your voltage. Then you can simply partial fraction it. This is what your voltage in the time domain. If you want to verify what will be the final value, then in both ways you can go. You can apply your T equal to minus infinity there, then your final value V infinity would be equal to 31.25 volt. or you can use your final value directly to this problem is equal to limit S multiplied by VOS, S multiplied by VOS, limit S tends to 0. So if we apply it, then you will see that your final value is there that you can determine from VOS without taking its inverse. Or even you can use your initial value there just to what you call just to verify that your formulation is correct. Can you do that? Your VOS is equal to 125. VOS is the voltage across this resistance. S into S plus 4. Actually, your VOS, what will be the final value, initial value? Limit S tends to infinity, S multiplied by VOS, isn't it?
Yes, sir.
Okay, the transfer function concept. You have already known this thing from your control engineering. Here your transfer function is actually defined for initially relaxed system. That means in order to find the transfer function, only the zero state input is used or zero state solution of your circuit is used, because zero input cannot be included there to find your Laplace transform, that transfer function that we have discussed earlier. What you need to do, we have to do, we can define our Laplace transform in this way, that it will be the ratio of input and output in the S domain, but your network must not contain any initial state in them. Your transfer function can be voltage gain if your output and input both are voltage. Your transfer function can be a current gain if your both of your Y and X are current, and it can be a form of impedance if one is voltage, your input output is voltage and input is current, and your ACS can be an admittance if your output is a current and input is a voltage. So you know this thing. Your transfer function can have these four different versions, but finding the transfer function is very easy. What you need to do, you find the ratio of output to input. This is a very simple example, that the linear system has an output equal to this, and when the input is X equal to this, find the transfer function of the systems and its impulse response. So how to do that? How can we find the transfer function? Your output is given in time domain, your input is also given in time domain.
Like convert to frequency domain first.
That means we have to convert our input into S domain and output into S domain. Then
Yes,
we
sir.
can easily transfer. This is, output is 10 e to the power minus t cos 4t ut. The Laplace transform is what? 10 into, because of this factor you have a delay there, S plus 1 divided by S plus 1 square plus this omega square, okay? And you know,
Yes, sir.
the Laplace transform of a factor, say a e to the power minus alpha t u alpha t cosine omega t is a s plus alpha divided by s plus alpha square plus omega square. So this is what the Laplace transform of a damping sinusoid. So this is your Laplace transform. Then you take the ratio. If we take the ratio, this is what your Laplace transform. Look at this thing. When you have a factor something like this factor is not a true fraction. Is it a true fraction?
No, sir.
Why? প্রাইমারি স্কুলের ধারণা প্রকৃত ভগ্নাংশ কাকে বলে?
So the numerator is greater than the denominator.
তাকে প্রকৃত ভগ্নাংশ বলে? প্রাইমারি
Okay,
স্কুল ক্লাস
then
5 এর পোলারে জিজ্ঞাসা করো, এই তোমার থেকে বেশি ভালো উত্তর দিতে পারবো। নিজেকে আর কোথায় নামাবা? কোন প্রশ্ন জিজ্ঞাসা করলে উত্তর এরকম হয় কেন? 1 ঘন্টা পর আনসার, কেউ কেউ ঘুমাইতেছে। Which 1 divided by 2 by 3, is it a proper fraction?
No, sir.
What does it mean? It means that if in the case of polynomial, if the order of the numerator is equal to or higher than the order of your denominator, then it becomes an improper fraction.
Yes, sir.
In your class 8, I learned it when I was in class 7 or class 8 probably, when I have been introduced with partial fraction.
It's a mixed fraction.
It is not a mixed fraction. Okay, try to use the language of mathematics, not devise something by your own. This is an improper fraction. What you need to do in order to get the improper, you have to divide your numerator by denominator in such a way that it becomes a proper fraction. So if we divide our numerator with that denominator, you see that we can easily do this in this way. You see that when they are of same order, in the case of real system, that will give you an output. That output will contain an impulse. You can easily say that the impulse response ht contains a factor 10. What is the Laplace inverse of 10? What is the Laplace inverse of 1?
Sir, delta.
If the Laplace inverse of 1 is equal to an impulse, then Laplace inverse of 10 is equal to what? 10, something like this. This is what the Laplace inverse of 10. And the rest of the thing is this. That means this network or this fictitious system contains an impulse response that also contains an impulse. Can you give me an example of a very simple example where your impulse response can have an impulse?
The numerator and denominator has same order.
সেটা তো এখান থেকে বাচ্চাও বলতে পারে বাবা। তোমারে তো বললাম একটা সিস্টেম বলতে, যেটা তুমি জানো। হোয়াট সিস্টেম ইউ নো? 18 লাখ টাকা দিয়ে পড়াশোনা করতেছে ইউনিভার্সিটিতে, তার আউটপুট যদি এই পরিস্থিতিতে হয়, পয়সা তো নিজে দাও নাই মনে হয়। আর আমরা বিনা পয়সায় পড়েছি। Okay, if this is your network, consider that we are giving an input access there, and we are want to find an output across this resistance. Say this output is VOS, and this is your CS. Then in the Laplace domain, R will remain unchanged. You C equal to 1 by CS. Can you find the transfer function? HS is equal to what? Your VOS divided by XS. What will be the value?
Sir, R divided by R plus 1 by CS.
R divided by R plus 1 by CS.
Yes, sir.
Very good. Now, if we have this inductance transfer function with us, can you tell me if we find the impulse response HT, will there be any impulse? Will there be an impulse? Okay, just reshape the equation in this way. It will be equal to RCS divided by RCS plus 1. Or even you can write it in this way, S divided by S plus 1 by RC. Is it okay?
Yes, sir.
Then will that will the impulse response contain an impulse?
No, sir.
No.
Yes, sir.
একজন কয় ইয়েস আর একজন কয় নো, আর বাকিগুলো কোথায়? লেপের নিচে ঘুমায় আসে। একটা ছেলে আনসার করে না, একটা ছেলে রেসপন্ড করে না, আর পরীক্ষার উপর পরীক্ষা নেওয়ার জন্য টিচারদেরকে ইনটিজ করতেছে তারা। একটা কঠিন পরীক্ষা দিলে নানা ধরনের কাহিনী রচনা করা শুরু করো, যে আমার এই হয়েছে, আমার সেই হয়েছে, এইটা যদি এত হইতো তাহলে এত করতে পারতাম, এই করতে পারতাম। দুই একটা ছেলে যারা রিয়েলি ভালো তারাই রেসপন্ড করে, তারাই ভালো করে। বাকিগুলো অবস্থা যে কি টের পাবা এবার পরীক্ষার পরে। অনলাইন হয়েছে মানে মনে করতেছে ইচ্ছা যা ইচ্ছা তাই করবা, অত সোজা নয়। কিছু কিছু টিচার তো তোমাদের অভ্যাস খারাপ করে দিয়েছে বহু আগে থেকেই। ফিজিক্যাল ক্লাস সময়ও অভ্যাস খারাপ করে দিয়েছে, মাথায় হাত বোলায় 12টা বাজাই দিয়েছে। টের পাবা ফিজিক্যালি যখন প্রফেশনে যাবা কি ক্ষতি করেছে তারা তোমাদের। So you see that very simple, you see your numerator and denominator order is equal. If they are equal, then what will happen? A constant term will be appearing in the factorization, okay? That will generate. But you can ask me a question that if the order of your numerator is higher than what, then what will happen? S term will be there. And actually this type of system is difficult to be analyzed by using Laplace transform. And in general, whenever we are using this system, we consider our system an LTI, and those type of system will generally either they will have equal order of numerator and denominator, or your general denominator order will be less than your numerator. Did you find this type of problem in your control engineering?
Yes, sir.
In which context?
Sir, solving electrical circuits by
Solving an electrical circuit by,
Laplace's equation.
sorry, by Laplace transform.
Sir,
Then this thing is actually a repeated version of our thing, isn't it? Okay, now we will be discussing something about network stability. We will not be considering, for example, variable gain system, that in the variable gain feedback control system, the network stability cannot be so easily understood by using the thing that we are going to discuss from this point ahead. I don't know whether you are there at your control system engineering, because 50% of the content of the control system engineering deals with system stability. Okay, are you using Raut-Harris technique?
Yes,
or,
sir.
Or
Yes, sir.
Nyquist stability?
Sir, Raut technique, sir.
You are in the Raut, okay? And you have to plot the root locus just to know in what ways your roots of your system functions are plotted in the complex plane. Actually, your root locus is nothing but a pole zero diagram. But in the root locus, the locus of the roots is actually traced by varying some gain parameters. Then you can easily identify that where your locus should be in order to have your response stable or viable. And even some error is there that you can easily calculate. If you have a controller you need to design, then this type of route can be manipulated. just so that your output response can be tractable, okay? And Nyquist criteria is another complex, it is called conformal type mapping, where a complex function is mapped from one plane to another plane. Then where some locus, some techniques are there that is called a technique of argument, by which you can identify whether your system is stable or unstable. But some general, but the basic is actually the thing that we are going to discuss now, because from this point ahead we have to start. Actually, what we usually do, if we have a transfer function obtained in the S domain, and you know that S is a complex variable, then what you can do, you can calculate the poles and zeros of your function that I have discussed earlier. Poles are nothing but the values of your functions where the value will be getting infinity. That is what that is actually the roots of your denominator. If you set ds equal to 0, then you will find some roots of your ds. At that roots, the value of your h will be getting infinity. And if you set this is equal to 0, then you will be getting some roots of ns where your functions are getting 0. If we plot them in a figure, that figure is actually a complex plane. That complex plane will tell you the nature of the stability of your system. Now the thing is that, as you know from your earlier tiny examples, that if we have a circuit, that circuit contains some poles. Those poles are actually related to system responses in such a way that the transient behavior of your system that contains exponential terms will be the principal factor of identifying the system stability. If we have, for example, say, if we have if we have an H, the transfer function of this form, this transfer function has numerator and denominator. Okay, if we factorize our denominator, then you will have, say, P1, P2 to Pn are the roots. Now the question is that your root can be there, as you know that if you have a polynomial, that polynomial can have roots, that roots can be distinct. That means they are not equal, they are separated. We have learned it during solution of what we call characteristic equation of a differential equation in chapter 2. Your roots can be repeatingly appearing. Some roots can be what we call distinct, and other roots can be complex conjugate. So in which case, if your roots are, say, distinct type, and the P1, P2, and Pn can be real or can be complex, or even can have only imaginary part. So if we plot them in the complex plane, customarily crosses are for the pole and zeros are for the zeros. So the zero and poles will be located there in the plane, something like this. And this case, you see that if we have, for example, you know that each of these term, say 1 divided by s plus say p1, that will generate a term e to the power minus p1t in time domain, isn't it? If
Yes,
this
sir.
is your time domain representation, then if your p is, say, real, and that p must not be negative because this is your negative already. So this can be actually, this thing can be understood better by putting a minus sign there, okay? Put a minus sign there. If a minus sign is there, then your output will be equal to P1T, okay? Then you will understand it. That in this case, you see that in order to have your system output or impulse response to be bounded in time, what restrictions should be there in P1? Your P1 can be can be real. If it is real, then it must be negative. If it is negative, it must lie in this half plane. Otherwise, because it will be in this negative part of the real axis. And if P1 can be imaginary purely, then it will be lying on the vertical axis. Then if it is a complex conjugate type behavior with a real part as well as an imaginary part, they can be placed there in this region. Because if they are conjugate, they will be appearing in the positive and negative half of this plane. Only the imaginary part will be negative. But this P with is complex conjugate with real part, that real part should be negative. Otherwise, your system response will grow indefinitely with time and eventually become unstable. So the stability scenario of your system is is for higher order, starting from the second order. If your system is passive, still you have this problem. But if your system is active, even a first order system can have unstable behavior if the Thevenin resistance of your system become negative. And I have discussed this issue in chapter 2 when we dealt with ordinary differential equation in dealing with our system. An example is there. You have learning this example from your second year, first year, I think, because this is a second order system and this is your impulse response. You can easily find the roots there. Then you see that these roots will influence the response of your system. And although this circuit doesn't contain any active element, but it is second order, okay, the values of R, L, and C will determine whether your system is stable or no, your system will always be stable. Is there any possibility that alpha can go negative? Is there any possibility that this alpha can go negative? Your alpha is this.
No, sir.
So a passive system can be oscillatory or under damped type responses, but it cannot be, it will always stable, okay? But if that network will contain some active elements in it that is represented by dependent sources, then depending on the gain parameter of your dependent sources, the system output can go unbound and eventually your system becomes unstable. Okay, this is a problem, very interesting one. You have to, okay, you see that that circuit contains a dependent source, isn't it? And that dependent source is a voltage source or a current source?
Voltage source.
What type of source is it?
Voltage source.
It is voltage source, but what type of voltage source?
The current dependent voltage source.
It is current control voltage source, okay? And you know the location of this current. This current I1 is actually creating this voltage. And we have a gain parameter K. That gain parameter K will influence the stability of a system, okay? If you want to find the current voltage, whatever you need from your circuit, you can derive, you have your two loops there. Your loop equations are there put into this form. There you solve for I1 and I2. If we can solve for I1 and I2 and investigate that what will be the value of I2 and I1. Okay, so if we put this form into this equation, what common factor will exist both in I1 and I2? For example, if you want to solve this equation, it is a simultaneous equation, put it into the matrix form, then we have to solve for I1 and I2. In both of your I1 and I2, which factor will be remaining common? If we have a matrix A and B, and we are writing, for example, something there, A, B, C, D.
So the determinant will remain
We have a
common.
factor X and Y. Then in solving your X and Y, which factor will be remaining common in both X and Y?
Determinants.
Determinant of what? Determinant of this coefficient matrix. So that coefficient matrix will be coming, determinant of this coefficient matrix will be coming as a denominator for I1 and I2. Because you know that the solution of X is equal to that determinant value into, you replace your variable, for example, your column 1 by A and B, Then you put your B and A there, B and D there, and find the determinant. Is it not the solution for X? As a result, what is happening? The denominator D is coming for in X and Y in both the cases. So that denominator in our case will be the function of S. If there is the function of S, then in terms of our system stability, we need to investigate the nature of the roots of the denominator of your transfer function. Then what you need to do, that is equivalently equal to what? You take the determinant of this matrix and find the roots. That will tell you that what values of K will ensure that your system will be stable. Okay, this is what your determinant. That determinant will be appearing as a denominator for your system response. No matter whether calculating transfer function, no matter whether you are calculating I1 and I2 in both the cases. So in this case, you see that this is what the case. How many roots are there? We will have 2 roots there. And you can easily see that we have a negative issues. That negative issues are related to this term, this factor. And when they become, if we want to find the root of this equation, can you find the root? That root is what? A first order system actually. Here no, what is the root of your, okay, this thing is coming in the denominator. So if we shape the equation in this form, then root of which term will be applicable for as a root of your denominator? Is it not this term? Because this will be, it is 1 divided by delta will be coming there. This SC will be going in the numerator side. So your thing is that S into R square C plus 2R minus K, put it equal to 0, solve for S, that is you P, put the root, okay? This is what this thing. Now you can easily identify when this, if your P is in our case, in accordance with our, that if your P is, for example, which is negative when K is less than twice R. Thus, we conclude that the circuit is stable when K is equal. Okay, when, because the factors there in this slide, it was written as S plus P. If the factors are in this form, then your P should be what? Your P should be positive. Otherwise, things will not be stable. Or if this is the case, S minus P, accordingly you can choose what will be the value of P. Okay, your P should be negative then for your stable cases. So you have to identify that for which values of K your P will be satisfying this regulation. So in this way, you can identify that which gain parameter will make your system stable. If you do not use that range, your system will be there. In your book, some examples are there with numerical values. Try to solve them. Okay, this is another example that find the value of beta that will make your system stable. But in this case, you see that no, what you call dependent voltage or currents are there. What you can do, if you say circuit is not something like this, you can easily calculate the Thevenin resistance that will give you whether it is negative or positive, that will tell you that whether your system will be going stable or unstable. This is another example to find the solution. You just simple, your network is transferred into S domain by element-wise transformation. Your inductance was carrying a current 2 ampere. For this region, your network, your inductance is there. Your capacitance was carrying initial voltage equal to 5 volt. So this is what your parallel representation of your capacitor. Then you see that your network, when you use parallel architecture, that network has how many nodes? How many nodes are there in this network?
2 nodes.
it has only 2 nodes, okay? So how many nodal equations you will need then? Only one nodal equation will give you the total solution. So you write your nodal equation, then solve for the output. That output will be in the AS domain. Then you take the Laplace inverse, that will give you the time domain solution. So that's it from my part. We'll be talking on top of it in the next day, and probably your next class will be the final, the last class, and we can have some review if you want. That's it from my part today.